So to continue on with our synchronous motors here, this would be the start of objective 4. So we talked about the construction, the advantages, the disadvantages, how that rotor locks onto the rotating field from the stator, what happens if we put too much load on it, it increases that torque angle. Again, to a point where if we put too much torque on it, we could actually rip it out of magnetic locking. Okay, so now what we're going to talk about, just to kind of break up the topic, is we're going to be talking about different loads on the synchronous motor. Okay, so when we talk about if we load it too much, what can happen? Okay, so that would obviously be the overload portion of this, but we'll go through these 4 conditions and talk about what the load effect has on the machine, and then also what varying the field excitation will do, and then we'll end up with power factor correction. Okay, so first off, we'll talk about these loads. So the different conditions we're going to look at are no losses and no load. And again, no losses would be a fictional scenario because there's always losses, but we'll talk about it ideally what would it look like. Light load and leading power factor, rated load and unity power factor, and then overload with a lagging. Again, just so that we have a concept here, these motors would never be operated at a lagging power factor. They would either be at unity or leading. Okay, so this overload, and again, overload is not a good word for us, unless I guess you're sizing overloads for a motor, but an overload scenario is usually a bad thing for us. Okay, so again, we're looking at potentially finding the current going through the armature winding. So this would be in the stator. That's where we're going to get our phase voltage from our supply. Then we have the generated, the CEMF, or the back voltage that's opposite that. And then the resultant, which would be the addition of the two. And then this is what we use to find our current. Okay. So we're not going to necessarily have specific values in here, the calculations, but we just kind of really want to look at the phasor diagrams as well. So again, let's first start talking about no losses and no load. So Egen, again, being at this 180 degrees here, again, not a real thing, okay? Every motor has losses, so this is purely theoretical. But if this perfect machine was operated at this condition, the resultant voltage would exist. So the following would be true. So the resultant voltage is 20 volts at 180, because the phasor sum of Egen and V phase. So Egen at 140 volts at 180 degrees and V phase at 120 volts at 0 are exactly 180 degrees. So when we add those vectorially, we actually end up with the difference of the two because they're 180 degrees apart. Because this is 20 volts more, that's where the resultant goes. Okay, but if we add them again in our calculator, we would see it's 20 volts at 180 degrees. Now what's important here is this relationship that we talked about previously between the resultant voltage and the armature current, this 90 degrees. Okay, so our current now is at 90 degrees. So again, with this purely theoretical scenario here, my E resultant causes armature current in the stator. My armature lags E resultant by 90. So here's my E resultant and show it lagging current by 90, which then it makes the I-arm lead the phase current here by 90 degrees. So now we have current in a 90 degree lead. So basically we have a leading power factor or a power factor of 0 because it's right at 90 degrees. Okay, so this is a pure 90 degree lead. Again, theoretically at no losses and no load. So at this point, we would just be having this motor in there purely for power factor correction. Okay, so at this point, it doesn't even need to have a shaft on it, an output shaft, because we are not driving a load, and it's called a synchronous condenser at this point, where we're just using it for power factor correction with this extreme lead of current. Okay. Next scenario, light load and a leading power factor. So we did have a lead before, so we still continue to have a lead, but we're going to put a little bit more load on it and see what happens to the resultant voltage and the generated voltage because of that. So the following is true for a light load and a leading power factor. So again, the resultant voltage is equal to the phasor sum of E gen and V phase. So of course there's no value of voltage here, but we would add E gen at its angle and V phase at its angle, and we get this E resultant. Now because we're starting to come off the 180 reference with the E gen, because again now we have a load, so that torque angle is increasing, it pushes E resultant, where in the previous example it was right here on the 180, so it moves it up as well. And again, with remembering that we're keeping this 90-degree relationship with our current and our E resultant, it rotates our current in the same direction. So all these phasors kind of just shifted in a clockwise direction this way. So again, E resultant causes current to flow in the armature. The impedance is inductive, so it lags the current, or lags the E resultant, sorry, by 90 degrees. And the I arm lags E resultant, but leads the supply voltage. So again, we still have this I arm lagging E resultant by 90 degrees, but in this case, still in regards to the phase voltage, I have a lead here, okay? And whatever this angle is, depends where this guy's sitting, by how much of a lead I'm going to be. But right now, the motor is loaded and operating at a leading power factor. So technically, even though it's driving a load, it's still potentially correcting for power factor because it's a leading motor load as opposed to a lagging, which most of our motor loads are. Okay, so again, light load brings our E-gen up off the 180, kind of shifts everything over, so we're not in as much of a lead as we had here, but definitely still a lead. So now we're operating, driving a load, and providing leading VARs. This next scenario, rated load at unity power factor. So again, these motors are designed to drive a load. That's where they're most efficient, is when they're at their full load amps, driving the load that they were designed to load. So that would be at rated load. Okay, so the following is true for rated load and unity power factor. So they've given us a torque angle of 30 degrees, which would be due to the load, an increased load. So last time we were at 10, so now we're increasing the load to its rated. And it's saying the sum of E gen, V phase equals E resultant. Okay, that's still the same. This value of voltage at this angle plus this value of voltage at this angle is going to give you your E resultant at its angle. I arm still lagging E resultant by 90, so we're showing that right here. I arm is in phase with V phase, so that is what's making us at unity power factor here, is my armature current and my armature voltage are in phase with each other. So no lead or lag, no difference between current and voltage here. So this motor is running at unity power factor with its rated load. Okay, so again, rated load, unity, lighter load, leading, no load, full lead, okay, of 90 degrees. This is the operating area we'd like to see this motor in, from unity to leading, okay? The next scenario is our lagging, and this is an overload condition where now we've put an increased load angle or torque angle at 60 degrees. Again, this motor has almost reached pull-out torque, which is when it stalls, so it'd be obviously overloaded and not running properly. So we do not ever want to see a synchronous motor in this scenario. So following is true for overload and lagging. The larger torque angle of 60 degrees is not a normal condition, again, the result of overloading. E resultant is now almost equal to V phase, so I arm is increased. So again, we coming off of unity with our armature current. Whenever we come out of unity, we're definitely going to have a larger current being drawn, because now we're having to cover some of the VARs as well. So with this addition of this E gen still and V phase, we get our E resultant, but now we're in this quadrant when we have to show this 90-degree relationship between E resultant and I arm. We can see that that puts our current into a lag. Okay, again, we're going this way normally, counterclockwise. So I'm going to see my phase voltage here, and then whatever this angle is later, I'm going to see my current. So it's showing current lagging my phase voltage. Again, we would never want to see a synchronous motor operating with a lagging current. Okay. The motor is operating with a lagging power factor. Again, overloaded scenario, definitely not something we'd want to see. Okay, so those are the 4 different types of loads. Now the module goes through and starts talking about the manipulation of the field excitation. So there is a note in your module too that says, before we move on to field excitation, when we just finished talking about the overload scenario, is the effect of DC excitation is mainly to change power factor, and its effect on torque angle is generally small enough to be ignored. So it's definitely going to have an effect on it, on this torque angle here, by changing our field intensity, which will definitely change this E-gen. Okay, but they're saying it's going to be smaller, and that changing the mechanical load is still going to have the greatest effect on torque angle. So it will have an effect, but again, not as much. So again, when we're talking about changing the field excitation, we're talking about the magnetic field that's on the rotor itself, spinning around. Okay, that rotor magnetic field is what locks onto the stator magnetic field for operation, so that rotor is running at synchronous speed. Again, what we have though is with that magnetic field spinning around on the rotor, it's going to cut across the armature windings in the stator and induce a voltage back into those. So those armature windings, again, they have the supply voltage going through, so that's our V phase, but they also have this E-gen going through them, okay, based on the fact that that magnetic field is spinning on the rotor and inducing a voltage back into them. Okay, so that's what this E-gen is. Okay, this is a generated voltage, or this could be called CEMF as well. Okay, and again, it's going to be at a torque angle based on the load. If we don't manipulate the load, it's still going to affect the torque angle by changing the value of the field excitation. Again, if I have more current through my field, I have stronger magnetic field, it's going to induce more voltage into the windings, in the armature windings. So if my field intensity increases, this value is going to increase. Okay, and then that changes the resultant and then thus the current as well. Okay, so let's look at the examples they've given us here. So normal excitation, synchronous motor operating with a constant mechanical load. Okay, so that's important there. We're not changing the load. Has a minimum line current at unity power factor. Again, another important point. When I'm at unity, I'm going to draw the minimum amount of current. Okay, because I'm not providing current to make magnetic fields, if you will. Okay, so when I'm at unity, I'm going to have the lowest value of current. So this 34.75, again, in this example, would be the lowest current I'm going to see. If I come out of unity, this value is definitely going to increase. Okay, with the armature synchronous impedance of 2 ohms, and the armature current is 35 amps at unity power factor, the excitation that results in the motor operating at unity power factor is called normal excitation. Okay, so whatever the value of current going through that, or creating that magnetic field on the rotor that produces enough generated voltage to make this E resultant rate at 90, which would in turn put our armature current rate at 0, is called normal excitation. So when we're at unity, the excitation value that created this is called normal. Okay. Then we talk about underexcited. So if the mechanical load again remains constant, we've reduced the excitation current. Okay, so we've dialed our potentiometer or whatever it may be, and we've increased the resistance, so we have less current, so our magnetic field on the rotor isn't as strong. We're not going to induce as much voltage back in those armature windings. So then the resultant voltage leans more towards the phase voltage. Okay, because it's larger, and again we can see an increase of angle here. Okay, but it's again it's small. We would say load is still going to be the biggest one here, but we want to see the effects of just the excitation. So with this different now changed lower value of E-gen, it moves the E resultant over into this quadrant and creates our lagging current again, because we have to maintain this 90 degrees with the E resultant. So when I came out of unity, you can see that we went from 34.75 amps to 39.46. So when I come out of unity, my current is going to increase. Okay, now its E resultant increases. Okay, so this value also increases from 69.5 to 78.92. And starts to get into this quadrant. So now our I arm lags at an angle of 28.7 degrees. So we have a lagging power factor of 0.885. So the motor is underexcited when the excitation results in a lagging power factor. So normal excitation, unity, underexcited, we get into a lag. Now the last one, overexcited, obviously you can see it gets into a lead, but let's look at the phasor and see why. Okay, again, a mechanical load remains constant, the excitation current is increased, Egen is now higher because if we increase the excitation current, we're cutting more lines as that's spinning around, and we're going to induce a higher value of counter EMF, which is this value here, this generated voltage. So it's larger now, so it pulls the resultant basically off of the 90 compared to the normal excitation, pulls it into this quadrant, which again will pull the current from, compared to being at unity, is now going to be into a leading scenario because this value of voltage is high. Okay, and it did change this angle here. So it will change it, but again, we want to see what happens with the load and the excitation, so we want to compare the two. And then when we're talking about this excitation, this value changes here. If that value changes, again, I like to use normal excitation as a reference. If this increases, it's going to pull everything over this way, increase the value of the resultant as well, and pull it off of the 90. But again, we still have to adhere to this 90-degree relationship, which pulls my current out of unity. Again, increasing the value here of current compared to the 34.75 at unity. And we see it increase to 38.1 amps at this angle. Okay, so as we keep going, getting into more of a lead, our current would have to get larger. We're going to maintain the same wattage here. I'll show you in one of the other graphs coming up. Okay, so that's the effect of changing the field. Normal excitation, unity, underexcited, lagging, overexcited, leading. Okay. And most synchronous motors are operated at unity, 0.9 lead or 0.8 lead. The field excitation controls the motor's operating power factor. With a constant mechanical load and changing the excitation, the in-phase component remains the same and the torque to the shaft remains the same. So I'm still able to drive the mechanical load, the wattage of that load. Synchronous motor that is operated without load at a large leading phase angle is used for power factor correction and also called synchronous condensers or rotary capacitors. They may not have an output shaft since their sole purpose is for power factor correction. In most cases, these motors have two functions in general: to operate at a leading power factor to correct power factor of a plant and to drive a load. Again, drive a load at a leading power factor. So some of the performance curves. So we got our V curve here. This is again what we're going to replicate in lab to show the difference between when we adjust the field current, whether we have no load, half load, or a full load. So some things we want to kind of look at here is when we see the lowest value of armature current, that's where we're at unity, okay? Because that's where we're going to see the lowest value of current. So at 0.8 field intensity, I'm going to see this lowest value of current for the no load curve. Okay, they do shift over a little bit here, but if we want to know where this is at unity, it's at the lowest value of current. That's where we're going to be able to find where the excitation value should be giving me normal excitation. So normal excitation, again, right down here, that would be at unity. If I'm underexcited, so less field current, I'm going to get into a lag. And if I have more field current or overexciting it, I'm going to get into a leading scenario. Okay, so we're going to replicate these V curves in our lab. The other curve they talk about are the bell curves. This is in regards to power factor and field current. Basically what it's kind of showing too is that under full load, it's going to take more excitation current for us to hit unity. Okay, and that's kind of shown here between the no load, half load, and full load. So here's our field current. We can reach unity with less field current on no load than we can with the full load. Okay, and this 0.8 here is just from your modules talking about 0.8 there where they give you some values. Okay. This current value is various levels of field excitation. Again, our reference here is 0. When we have our current in phase, we're at unity. That's where we're going to draw the lowest value of current. You can see as we get into our leading, or we're over-exciting our field, the value of current has to increase, but this constant power line is always met with the current. Okay, so we're always going to be able to keep that, that load power that we need to drive that mechanical load, but we potentially will have to increase the current to provide for magnetic fields, whether we're leading or lagging with our VARs. Okay, so there is that constant power there still, but we do have to change our current to maintain that if we get away from our unity. Okay, again, over excitation, we're going to get into a lead. Under excitation, we're going to get into a lag. But again, we would not want to operate in this area. So then they go through and just do some examples of power factor correction. Again, I know you guys have gone through this, I think, for 3 years now. So I usually go through this on the board. I went through one in class the other day. So go through those examples. They do a solid job of going through and telling you how to do the power factor correction. They include some efficiency calculations as well for our motors, whether inductors, or like squirrel cage induction motors, or whether they're synchronous motors. Again, don't forget that it's still a motor. It does have watts, even if it's a synchronous motor. It's just the difference is the VARs are leading. Okay, so go ahead and get through some of those questions. If you have any questions for me, let me know. Otherwise, we'll do some examples as well when we're back in lab.